Once airborne, an aircraft functions as a closed, interdependent ecosystem. To sustain flight, the engine must continuously draw from three highly regulated resource flows: combustible liquid, direct current electricity, and high-speed air. The stakes for this internal logistics network are absolute. Interrupting any single one of these streams rapidly degrades the aircraft's capabilities. By mapping these three core systems from the ground up, we can trace exactly how they overlap and where engineers built in critical failsafes. Understanding this architecture transforms a pilot from a passive operator into an active diagnostic manager. The primary physical constraint of the fuel system is continuous delivery. The engine requires a steady, vapor-free supply of combustible liquid, regardless of changes in altitude, banking attitudes, or severe turbulence. That delivery begins in the wing tanks. To prevent surging, tanks utilize internal baffles to compartmentalize the fluid. Inside, the supply line enters through a standpipe above the absolute bottom. Denser water and sediment sink past the standpipe, pooling safely into a separate sump. As the engine burns through that volume of fuel, an atmospheric vent at the top of the tank equalizes the internal pressure. If that vent blocks, the engine pulls a vacuum, starving itself of fuel and potentially collapsing the entire tank structure inward. How that fuel reaches the engine depends on the airframe. High-wing aircraft can rely on gravity to feed the lines, but low-wing designs place the tanks physically below the engine block, requiring the fluid to actively fight gravity to reach the cylinders. This altitude deficit requires mechanical intervention. Low-wing aircraft utilize an engine-driven fuel pump, backed up by an independent electric auxiliary boost pump. Whether utilizing the physics of a gravity drop or dual-pump redundancy, the fluid architecture is shaped to eliminate single points of failure in the supply line. Mechanical delivery only works if the chemical resource is correct. Different piston engines require specific grades of aviation gasoline, matched to their compression ratios to prevent internal detonation. To ensure the right chemistry, the industry relies on a strict visual color coding system. The standard fuel for modern light aircraft is 100 low lead, which is dyed a deep blue. By contrast, turbine Jet A fuel is clear or straw-colored. Pumping turbine kerosene into a piston engine destroys the combustion cycle, making cross-contamination at the tanker truck a catastrophic error. You also cannot substitute unapproved automotive gasoline. Autogas is chemically blended to be highly volatile, meaning it vaporizes easily. At altitude, that volatility creates vapor locks, pockets of air in the supply lines that instantly starve the engine. Even with the correct grade, pilots perform a physical check before every flight. Because temperatures drop overnight, condensation forms on the inner tank walls. Pilots drain a small sample from the sumps directly into a clear cup, looking for that denser water settling at the bottom. Rigid color coding standards and manual visual inspections protect the mechanical system from chemical contamination. The next required flow is the electrical grid. Most modern light aircraft operate on a direct current, or DC system, typically rated at 14 or 28 volts. The central bus bar is the conductive spine of the grid. Initially, the battery pushes massive amperage to crank the starter motor. Once firing, the engine-driven alternator takes over the entire electrical load, while pushing a reverse current to recharge the battery. However, an alternator has a strict engineering constraint. It cannot generate its own starting current. It relies on a residual voltage from the battery to excite its internal magnetic field before it can produce a charge. Pilots control this relationship via a split master switch. This dual mechanism allows you to isolate the battery and the alternator from the bus bar independently, sealing off specific circuits in the event of an electrical fire or component failure. But there is a crucial exception to this grid. The master switch does not control the engine's spark plugs. The ignition is powered by completely independent, engine-driven magnetos. Because the magnetos generate their own electricity from the physical rotation of the engine, a total collapse of the electrical grid will kill your radios and lights, but it will never stop the engine from firing. Cockpit ammeters provide real-time diagnostic data regarding the flow state of the busbar. This is a left zero ammeter, or load meter, measuring total alternator output. If this needle drops to 0 in flight, the alternator has failed, leaving the aircraft entirely dependent on the reserve capacity in the battery. Conversely, a center zero ammeter tracks whether current flows into or out of the battery. Tilting right means safely charging. If it deflects left, electrical load exceeds alternator supply, and the battery is actively draining to compensate. In the discharge state, the pilot must intervene. By systematically shedding non-essential electrical loads, like secondary radios or cabin lights, the load is reduced until the alternator can recover the deficit. Reading the specific mechanics of these needles give pilots the data they need to preemptively manage power deficits before the system goes dark. While communication runs on electricity, the aircraft's spatial awareness relies on a completely different flow. Core gyroscopic flight instruments are powered entirely by pneumatics. Instead of pushing air in, the system pulls it out. An engine-driven vacuum pump continuously evacuates air from the sealed instrument cases, creating a very significant pressure drop. To fill this low-pressure void, ambient cabin air gets sucked through a filter and forced across internal gyro buckets. This highly directed airflow spins the heavy rotors at speeds exceeding 20,000 RPM. Modern aircraft use internal engine pumps for this suction, but older designs relied on Venturi tubes mounted outside the fuselage. Those tubes leveraged Bernoulli's principle, using the forward airspeed of the aircraft to drop the static pressure and pull air out of the instruments. By spinning vital navigation components with raw pneumatic pressure instead of direct current, engineers established a parallel, completely redundant path for situational awareness. If the electrical grid fails, the gyros keep spinning. Zooming out, the complete architectural ecosystem reveals itself. The spinning engine block is simultaneously pulling resources through 3 separate networks. That mechanical rotation is the primary driver for everything. It powers the vacuum pump for the gyros, the primary fuel pump for the liquid supply, and the alternator for the electrical grid. In return, those systems feed the engine back. The electrical grid powers the auxiliary boost pumps to prime the fuel lines and drives the starter to initiate the combustion sequence. Yet within this tight web of dependence lies the system's ultimate failsafe. Thanks to independent magnetos and the physics of gravity-fed fuel, the internal combustion sequence survives the total collapse of the electrical grid. Because these systems overlap seamlessly in the background, a pilot cannot physically feel which pump or battery is bearing the load. Cockpit indicators and ammeters are the only empirical proof of system health. Recognizing the hardware logic behind those indicators is the foundation of aviation safety. It explains exactly why emergency checklists dictate specific actions in a crisis. The airframe architecture utilizes these overlapping layers of redundancy to ensure that the aircraft maintains flight even during a partial system failure.